Okay, I am going to try to do problem number 11 so that it gives you a clue about how to do number 12. In this problem we have a square wafer or wafer if you watched Father of the Bride. 15 millimeters on a side. And we're wondering what is the rate of change of this as it grows by some delta x. Alright, so this is the original 15 by 15 wafer. Alright, of course the area based on its dimension x is going to be x squared. Alright, so a prime of x is a very straightforward 2x. And we are asked to really look at this and think about it geometrically, I guess, in the second part. Also to show that it's half the perimeter. Well, the distance around that, by definition, the perimeter there is 4x. So we can see that that's equal to 2x is equal to 1/2 of 4x. Alright? So the derivative or the rate of change is just equal to 1/2 of the perimeter. Alright? But then this whole idea of giving it units, I guess it would be to say that this rate of change is in millimeters squared per millimeter of growth as this expands from here out to that amount delta x. It's growing at a rate of 2x square millimeters per millimeter of growth along one dimension. Alright? It helps because when we think about this geometrically, this area here is going to be a rectangle that's bounded by delta x and x. So that area there is just simply x times delta x. Well, that's going to be the same as this area here. That's just x times delta x. So if we sort of ignore this little bit here, which instantaneously is a very, very small amount, really the change in area is 2 of these. So we have 2x delta x. And then if we say, well, that's per delta x, really you can see that we can think of this as being 2x as our rate of change for the growth of that area. Alright, problem number 12 is very, very similar, only we're going to 3 dimensions. Alright, so we've got a cube and we're given some fixed dimension, alright, and if it's expanding, if it's growing at some rate out in this direction, it's also going to be growing up like that, and it will be growing back. We can think of this that way. And so there'd be this extra layer of growth that's going like that, and then behind it you could think of it as a sort of a 3-dimensional shape of growth, and like this, and back here. And then also lifting off would be above it, and I'm separating this just so we can see it, would be some amount there. So we'd have this amount of extra volume, this amount here of extra volume, and then this amount here of extra volume. So of course the volume based on x is going to be x cubed. Alright, so I'll leave it to you to find, well, what is v prime of x and all that. But then if you think that these extra amounts are added on, you can pick any corner you want to sort of grow away from. I've picked this corner to be our reference point. It's growing away in that direction. It's growing away in that direction. This cube is growing away in that direction. You'd have these 3 surfaces. Total surface area, there are going to be 6 surfaces. If you think of it as like an area of a die, you've got your faces of your die lining up. You've got 6 of these faces while it's really growing in 3 dimensions beyond that. That leads to the 3:6 ratio that will help you answer that question for problem number 12. Hope that helps. There you go. Okay, I'm just going to give you a couple of hints on a few more of these problems. A lot of them you just need to be confident that you're working with some simple derivatives on some kind of complicated, perhaps looking, real-world type of equations. Number 18 is an example of that. We've got this equation that will govern model the draining of a tank hole at the bottom. the water pressure is greater at the beginning, so it's going to force more water out. As it gets down to last drip, it'll be a lot less pressure and a lot less quickly its draining rate. So this is the volume. I guess we could say V of t. It's based on the time. V prime of t then is going to be relatively straightforward. This is just a constant. You kind of remove that. Then take the derivative of this part. Well, the 2 will come out front, so it becomes 2 times the derivative. Don't mess with the inside. That's the chain rule. And then times the derivative of the inside, which will be minus 1/40th. Okay, if we do some cleaning up, 2 times negative 1/40th will be negative 1/20th. Cancel a 0. 1/2 of 500 with the negative sign is negative 250, then times 1 minus 1 over 40t. Okay, so that is the rate at which water is flowing out. You can plug in different values. I think that's what they ask you to do, so you can see how that works. Do they ask anything else? Let's see. I think that it makes sense that it will flow out the fastest. If you think about this at the beginning, when that's 0, and it's going to flow out then at a negative 250. When it gets close to being empty, 40 seconds later, then you'll see that that is going to be very close to a rate of 0. So that makes sense. Okay, hope that helps. Number 20, similar in that you've got this equation. In this case, one of my all-time favorites. This is Newton's law of universal gravitation. The equation, I'm writing it slightly differently here. M times capital M all over r squared. These are the two masses of the objects, and you can look up and see how that was originally measured, because you think of how difficult it is to determine the constant that measures the gravitational pull between two objects unless you have two objects that you can measure independently. And in fact, I think Newton or someone shortly thereafter did it with 2 huge iron balls that were suspended, and they could actually measure the gravitational attraction between these 2 gigantic iron masses. Anyway, in this case, it's only r that's varying. We're not going to be able to change the mass of objects very easily. So what is this based on r? We can rewrite this in a sense as that gravitational constant times the constant mass and the constant mass of the other object. So this is all one big, in this particular question, constant times r to the negative 2. So when we go to take the derivative of this, f prime of r, then you're going to see it's that same GMM, but then it's going to be times negative 2r to the minus 3. Well, that will just be the same thing as before, but negative and then 2 GMM all over r cubed. Okay, so the change in the force is going to be governed by this equation. And then they give you an example. They say, suppose we happen to know that at some distance of 20,000, is it meters? It must be meters or kilometers. Kilometers, so big distance. That the force then is decreasing. So that's, I guess they want you to comment on, what does that negative sign mean? Well, that's that as 2 planets, 2 objects, 2 whatevers are getting farther apart, the gravitational force between them decreases. And it decreases by the cube of the radius. All right. If this is decreasing at a rate of 2 newtons per kilometer, Newton is a measurement of force, kilometer is distance, what's going to be the case when you cut that distance in half? Okay. Well, you can work out what GMM is and work out that constant, but it's very simple just simply to say, what is the change in as a ratio? Well, the distance between those 2 objects, the 2 masses, M and M capital, this decreases by a ratio of 2 to 1. So what's happening to that radius, the force, as it decreases by 1/2, will be then cubed. All right, and in this case we're inverting it, so it'll be to the minus 3. So it actually becomes 8 times stronger. All right, if you multiply that by itself 3 times and flip it. So we just simply multiply that by 8, and it'll be a negative 16 newtons per kilometer. So when these two objects become twice as close, in the beginning there's the planet, right, and there's the satellite, and that distance there is some r. If you bring them half that distance and then let it change, the decrease will go up by a factor of 8, by the cube of the radius. All right. In 28 then, similar kind of a thing, that we have this equation that governs the frequency of a plucked string based on several factors, and we're going to change each of those factors. I think the book takes you through it. That the equation looks like this. I think that's the tension, and this is rho, and that is the linear density of the material. If it's a plastic guitar string versus a metal string, spring steel string, or whatever. And they take you through each of these three things in turn as it changes. I think it's very helpful to think of this as 1/2 then times L to the minus 1 times T to the 1/2 times then rho to the minus 1/2. Okay, that's a half. And so each of these things, if it's held constant, you can just think of like this as being a constant. So in one part, when they say, well, what's happening as this is changing? You just take the derivative with respect to this. So f prime in terms of rho will be then 1/2. These are all constants. They do not change. L to the minus 1 and T to the 1/2, but then times negative 1/2 rho to the minus 3/2. Okay? And so what's going to happen as this... Okay, so we've got the derivative, and if we consider rho as being the only variable there, remember rho is in the denominator, so if we get a negative derivative, then that means it is decreasing as rho is increasing. So as this linear density gets greater and greater, it'd be difficult to think of a way that it could do so kind of continuously. Usually you're just replacing one string with another string or whatever. But if you could imagine it somehow changes, that negative means that the frequency is decreasing, and as that decreases, the note gets lower and lower and lower. There you go. Hope that helps.